Good afternoon, everybody. Welcome to the latest in our series of webinars. This webinar is Humidification and Psychrometrics. Firstly, thank you very much for joining. So my name is Dave Marshall-George, and I'm the UK and Ireland Sales Director for Condair. And with me, you'll see on your screen is Anthony Hall, and Anthony is the Area Sales Manager for in the Midlands for Condair. And I'm going to be delivering the main presentation, and Anthony's going to be dealing with any questions in the background. So the webinar should last about 45 minutes, and then we've got a 15-minute section for Q&A at the end of the presentation. And you'll see on your screen that there's a go-to webinar control panel on the right of your screen where you'll find the audio options, and there's a questions tool. So if you do have any questions, it's better to put them in, as you think of it, and then either Ant can deal with it or I can deal with the questions right at the end. There are some handouts that you'll see in the control panel as well. There's a 10-point guide to psychrometrics and specifying humidification. There's also a copy of the presentation. I'll be turning off my camera during the presentation so you can just concentrate on the slides. And following the session, after about an hour, all attendees will receive an email and a certificate to say that you've been live on the webinar. So without further ado, we're going to turn our cameras off and we will dive into the webinar. So I mentioned Condair. We work for Condair. Condair are the biggest humidifier manufacturer in the world. We manufacture out of 4 manufacturing sites, one in Ottawa, one in Hamburg, one in Denmark, and one in Beijing. We currently have about 720 staff, and we distribute globally. So what we're going to be looking at today is why you would want to humidify in the first place. I think it's a pretty good place to start. Then we're going to look at the psychrometric processes, both adiabatically and isothermally, and understand how we use the psychrometric chart to design both adiabatic and isothermal systems. We're then going to look at load calculations, so you can work out how big your humidifier is going to be. And then we're going to take a cold, hard look at the different humidifier types that are available to you and the pros and cons of applying them. So to start out with why humidify, well, we kind of split these into 3 categories. And the first one is improving productivity. Now, there are hundreds, if not thousands, of applications that we get involved in where we're improving productivity. And that could be anything from a printing application where we're preventing paper expanding and contracting and curling up and fouling machinery and making sure that ink dries in the correct fashion. It could be an abattoir where we're humidifying animal carcasses during the cool down process to prevent weight loss. Of course, meat is served is sold by weight, so we increase the efficiency of the abattoir. It could be a bakery where we're humidifying the dough proving cycle, or indeed putting steam in to make sure that we get the correct shine on the crust. It could be a spray booth to ensure that we don't have too thickness a level of spray, or indeed to make sure that drying times are correct. There could be any number of these factors that there really is something new every day that we come across where we're controlling the moisture content in air. Preservation is also a big part of our business, and this could be a museum, it could be a church organ, it could be a stately home, somewhere where we've got valuable hygroscopic materials that will expand and contract with a change in moisture content. Now, that expansion and contraction can cause a tremendous amount of damage, and in fact, you can see more expansion and contraction with a change in moisture content of the air than you do with the change in temperature, believe it or not. And this expansion and contraction, as I mentioned, can cause a tremendous amount of damage. And one of the worst cases I saw was in a museum in the Midlands a number of years ago now, where they got a 15th century Flemish oil painting. It was oil painted on board. And this thing had expanded and contracted until it could do no more, and it split from top to bottom, just off the centre. Almost enough to get your little finger in there. It can cause a priceless amount of damage. But in fact, a museum can't accept a travelling exhibition and be covered on its insurances unless they can demonstrate that they've had a stable temperature and relative humidity for 3 months before they accept that exhibition. So it's critical with museums, libraries and archives, conservation rooms, church organs, with expensive wooden floors. We see all these kinds of applications. And thirdly, there's humidifying for health and infection control. And it was right for us to kind of examine this in a little bit more detail in light of the pandemic. And the current knowledge is that there are 3 ways that maintaining relative humidity between 40 and 60 has a positive effect on the body. Well, the first one is our respiratory immune system efficiency. So in a dry indoor environment, the respiratory immune system's defenses are impaired. And that allows viruses to infect us more easily. Whereas between 40 and 60% RH, the respiratory immune system's defenses function much more effectively, and we capture or remove germs or those airborne pathogens. So what's actually happening here is the cilia, which are little hairs in your respiratory system that float in a mucous membrane. When that mucous membrane gets dry, it doesn't work as effectively. So we don't capture as many airborne pathogens. So maintaining that indoor air humidity between 40 and 60, we're helping our body do as efficient job as it can to capture those airborne pathogens. Next is the virus float time. So in a dry indoor environment between 0 and 40% RH, airborne droplets containing viruses shrink by evaporation. That means they're lighter, so they float for longer. Whereas between 40 and 60% RH, airborne droplets containing viruses will retain their moisture. It means they're heavier and they'll fall out of the air quicker. So you're exposed to the airborne pathogen for a shorter amount of time. So that can only be a good thing. And then finally, there's the virus survival time. So it gets a little bit more complicated here. Where between 0 and 40% RH, airborne droplets containing viruses allows the airborne droplets will dry, and that allows the virus to survive for longer. Whereas between 40 and 60%, airborne droplets containing viruses retain moisture, and that allows a physiochemical reaction to deactivate the virus. Now, I'm not a biological chemist, but if you are interested in the white paper that goes through this, then you can find links to that on our website. So please feel free to dive in and have a look around. Now, a nice way to illustrate this is this diagram that you've probably seen before. It's the EM Sterling criteria for human exposure to humidity in occupied buildings. And it's straight out of the ASHRAE handbook. And this shows the proliferation of airborne pathogens, bacteria, viruses, fungi, mites, allergic rhinitis, respiratory infections, chemical interactions, and ozone production at different proliferations of relative humidity. So starting at 0 and going up to 100. And you can see that if you take viruses, for instance, there's a high proliferation at 0, and then it tapers down and drops away. And there's a sweet spot between 40 and 60 before we start to see it increase at the higher levels of relative humidity. So it is really between 40 and 60 that we're looking to maintain our environment. Now, there are lots of recommendations when we look at ASHRAE, the Academic Task Force. They were recommending 40 to 50 or 40 to 60% RH. European Centre for Disease Prevention and Control, again, recommends relative humidity between 40 and 60%. And we can see these recommendations throughout the world, but there is no legislation that stands behind that. It's something we need to educate our customers that between 40 and 60 is the optimum relative humidity for us as human beings. So there's some of the reasons why we humidify. Now, next we're going to look at the psychrometric chart and how we plot out the processes that are involved in both adiabatic and isothermal humidification. And I'm sure many of you will recognize the psychrometric chart, but forgive me, I'm just going to run through the basic elements of the psychrometric chart for you. So the first thing that we look at is the dry bulb temperature, shown in degrees centigrade, and it's running from -10 up to 60 degrees C. Maybe a little bit small for you to see on your screen, but there we go. We go from -10 right up to 60 degrees C. And if you stick a thermometer on the wall, that is the temperature that you're going to read. But there is another temperature scale on the chart, and it's going diagonally down the chart. That's 20 degrees, 21, 22, 23, 24, 25, but 20 degrees wet bulb. So we have a dry bulb temperature and we have a wet bulb temperature, and they're not the same. So why do we have a dry bulb and a wet bulb temperature? Well, we have them because using those two temperatures determines other factors of conditions of the air. So it determines the moisture content, the relative humidity, the specific volume, and the specific enthalpy. By knowing those two temperatures, we can plot out all of those other conditions. So why do we call them a dry bulb and wet bulb temperature? Well, this goes back to the days before digital instrumentation. If you wanted to know any of these factors, you used an instrument called a whirling or a sling hygrometer. And a whirling hygrometer, you whizzed it round in the air, and a bit that you're whizzing around in the air had two thermometer bulbs in it. One was dry, and that will give you your dry bulb temperature, same as sticking your thermometer on the wall. But the other thermometer had a linen wick over it that was wetted by a small reservoir of water. And the theory is that if the air is 100% saturated, no evaporation can take place off that wetted wick and have a cooling effect on the thermometer. So we know where the air is 100% saturated, those two temperatures would be the same. And you can see that on the psychrometric chart, because if we have 20 degrees C dry bulb and 20 degrees C wet bulb, we can see we are at saturation. So this is our saturation curve, or dew point as it's sometimes called. That's 100% relative humidity. And we can see the humidity falling. There's 90% RH, 80% RH, 70, 60, and 50, and so on. All about percentage saturation. So let's say we've got a condition of 20 degrees C dry bulb and 14 degrees C wet bulb. We can see that we're at 50% relative humidity, so we can read it off the humidity curve. What else can we read from the chart? We can read the moisture content. So if I'm at 20 degrees C dry bulb, 14 degrees C wet bulb, 50% RH, I can read across I'm something like 0.007476 kilograms per kilogram of dry air. So I can tell the absolute moisture content, or sometimes referred to as absolute humidity, the actual moisture content of air. What else can I read? I can read the specific volume of air in meters cubed per kilogram. So there's 0.85, 0.86, 0.87, and so on. There's 0.9. So going back to our condition of 20 degrees C dry bulb, 14 degrees C wet, 50% RH, I'm right on 0.84 meters cubed per kilogram. And then finally, we can read the specific enthalpy. So how much energy is in air at any one point? And I do that simply by plotting a line intersecting my condition, starting on this scale, intersecting my condition, and going down to the scale at the bottom. And where the value of the bottom scale and the top scale is the same, will tell me the specific enthalpy at that point. And I'll need to be able to draw that as a process in an adiabatic situation. So that's all a bit academic there, the basic elements of the psych chart: dry bulb temperature, wet bulb temperature, moisture content, specific volume, relative humidity, and specific enthalpy. So what do we do with it? Okay, well, the great thing about it is we can draw a process on the psychrometric chart and find out what happens to the air when we do that. So let's say we're going to heat the air up just by dry sensible heating. So if we apply sensible heat to the air, we're going to see a process similar to this, where we see an increase in dry bulb temperature. We see a decrease in relative humidity, though. There's 40, 30, 20% RH. But we haven't taken any moisture out, or indeed put any moisture in. So the absolute humidity will remain the same. So that's our heating process line. Next, a little bit more complicated, is isothermal humidification. So with isothermal humidification, we are putting steam at atmospheric pressure into the air. And when we do that, we have a vertical process line that climbs up the chart. And here you can see you've got an increase in relative humidity, that's 40, 50, 60, 70% RH. You can see that there's an increase in moisture content. That makes sense, we put steam into the air. But interestingly, and a little bit misleadingly, we don't see a change in temperature on this plot. And in fact, the literal definition of isothermal is no change in temperature, like an isobar, no change in pressure. Isothermal, no change in temperature. But actually, it's not strictly true. You will see a slight increase in temperature from isothermal humidification, and it will come from two sources. You'll get a small bit of residual heat from the steam, but you'll also get some residual heat from the steam pipe. So the method of steam introduction is a stainless steel tube with holes in. It's got steam in. It's going to get hot, so there will be a radiant heat source in the airflow. Typically, you'll see 0.5 to 0.7 of a degree increase in temperature from isothermal humidification. Dehumidification is differently. If I'm going to take moisture out, I could have a descending line such as this. As we dehumidify, we get a decrease in relative humidity. There's 40, 30, 20, 10% RH. We'll see a decrease in moisture content, but we'll always see an increase in sensible heat, in dry bulb temperature. Now, if we're doing direct expansion dehumidification, you're going to see a line similar to this. If you're doing desiccant dehumidification, you'll be following the adiabatic process line, which is more along the wet bulb temperature scale. So we have to be careful that we're applying the right psychrometrics to the right method of dehumidification. If we're cooling, well, if I'm mechanically cooling, I could see a right to left process line such as this. And the effect here is that we see a decrease in dry bulb temperature. We'd expect to see that because we're cooling. But we also see an increase in relative humidity. There's 40, 50, 60, 70% RH. But even though we're seeing an increase in relative humidity, I could be seeing a reduction in moisture content if I'm doing any latent cooling. So if I'm going through a DX coil, a direct expansion refrigeration coil, I could be sending the air below its dew point and reducing the moisture content. So I maybe want to be aware of that. Finally is adiabatic humidification and cooling. Now here I'm doing one of two things. I'm either passing the air through a wetted media that's porous and evaporating the water off that material, or I'm spraying water in a very small aerosol, a droplet-sized aerosol, into the air and letting it evaporate. And when I do that, I follow the line of enthalpy. So the line that we drew from this scale, intersecting our condition, to the bottom scale, and again, the angle of that line will be dependent on the value of the top scale and the bottom scale being the same. And that gives us this line that we draw as our line of process. So as we're evaporating water into the airflow, changing its state from a liquid into a gas, we're sucking heat energy out of the air. It's cooling. So the effect on the sign chart shows us that we get an increase in relative humidity, that's 40, 50, 60, 70, and so on. There's an increase in moisture content, shown in kilograms per kilogram of dry air, but I also get a reduction in dry bulb temperature. I am cooling. And again, it's because the basic thing that we're doing when we're humidifying is we're changing the state of a liquid from a
like that. I think we may seem to
liquid into a gas. Now, for the observant, the enthalpy difference in isothermal process, no difference between the energy required for an adiabatic system to an isothermal system. And we'll see that a little bit later when we plot out the two processes.
We can still see your screen, Dave, if you can hear me.
I can still hear you, yep.
Yeah. Do you want to relaunch the presentation? There you go.
There we go. Great, sorry about that, guys. We had a bit of a blip my end. So here you can see the evaporative cooling strategies. We mentioned that we've got a change in temperature. Whenever we've got a change in temperature, there are ways that we can utilize that. And in this slide, we can see that there are two ways that we can do it. We can do it either directly, or we can do it with exhaust air evaporative cooling. So when we're doing direct evaporative cooling, all we're doing is we're taking the fresh air and then we're running it through the filterer and then over a humidifier. We're cooling the air, it's evaporatively cooling, and then we send that into the space. And that's pretty straightforward. We then send that humidified air straight into the space and it's cooled down. And then return air comes away from the unit and then goes to exhaust. Now, the interesting thing here is it's only useful really if you've got low relative humidity at the start of the process. Because if we've got high relative humidity, it doesn't allow me to evaporate much moisture into the airflow. So I'm kind of limited on direct cooling. But there is another way of doing it. I can take my fresh air supply, I can then run it over a heat exchanger that's been cooled by humidified air. So we've taken moisture out of the air and we've put moisture into the air, evaporated water into the air and taken heat energy out. So I'm cooling the airflow. So by crossing over those two, I've got a cooled heat, surface there that I'm then going to send into the supply air. So by exhaust air evaporative cooling, I can on the. So I want to go back to, if you're going to plot out the isothermal humidification, the first thing I want to do is increase my dry bulb temperature to allow that humidification to occur. So I need to increase my dry bulb temperature to my start condition. Once I've got my start condition, I can then isothermally humidify to get up to my set point. So again, that process line is from my set point straight up to the condition that you require. And that's going to tell me a moisture difference. And that moisture difference is we're going to need to know that to do a duty calculation. So that's my isothermal. I need to preheat to my condition and then isothermally humidify up to my set point. With adiabatic humidification and cooling, I've got to start in a different place. Because the very nature of adiabatic humidification and cooling is that I'm going to be using the heat energy of the air to change the state of the liquid. So I need to preheat the air to a point where I can then rely on the adiabatic process to take me back to my set point. So in this case, I'll need to preheat the air from, let's say, -6 saturate up to 32 degrees C, and then follow the adiabatic process to get me back to, let's say, 21 at 50. So a reminder, we're going to be following that line of enthalpy. Of course, if I draw that line back to my start condition, I'll then humidify up to 21 at 50. So once we've done that, we've decided whether we're going adiabatic and isothermal, we can then look at a load calculation. To do a load calculation, I need to know some data. And the first thing I'm going to want to know is, well, how much air are we actually humidifying? So typically we use the units of meters cubed per second. So we want to know the outside air volume, not necessarily the total air volume, because we'd only humidify the fresh air makeup. So we want to know the amount of fresh air that we're humidifying. So for instance, if you've got a 90% recirculation, we're only going to be humidifying 10% of that air because all the rest of the moisture will be retained. We'll want to know the external ambient, and it's pretty common to be around -6 saturated at 100% RH. And we'll want to know the entire internal design condition, 21 at 50, let's say. So from our site chart, we can then establish that there's a moisture difference between those two conditions. And here it's pretty straightforward. Moisture content at -6 100 is 0.0022 kilograms per kilogram, as against 0.0078 at 2150. So I've got a difference there of 0.0056 kilograms per kilogram of moisture that I need to add to the air to get me to my condition. And I'm also going to want to know the specific volume from the critical part of the process, not necessarily your supply air temperature, because those two could be different. So our calculation is pretty straightforward. We take the outside air volume, meters cubed per second. We multiply that by the moisture difference in kilograms per kilogram of dry air. And then we multiply that by seconds per hour. And then we take that and we divide it by the specific volume. So here we go, we've got 1 meter cubed per second times 0.0056 kilograms per kilogram times 3,600, because we've gone from meters cubed per second to kilograms per hour, and we divide that by 0.84. This gives us a pretty good rule of thumb, because the answer to that is 24, just over 24 kilos an hour. Rules of thumb are pretty useful, actually. In fact, we've got 3 rules of thumb here. That's the first one. For every meter cubed per second of fresh air, going to give you 25 kilograms of humidity required. And for every 100 kilograms of steam you're providing, electrically, it's roughly 75 kilowatts of electrical power that's required. And interestingly, for every 1 kilo of cold water evaporated, that is going to take out 680 watts of heat energy from the air. Now, you may think that actually that rule should be the inverse of the other. But when you're producing steam electrically, then there are losses. You'll get thermal losses. It's not like you're sucking the heat energy out of the air. You're changing the state of the liquid, and you will get residual heat losses. So 75 kilowatts for every 100 kilograms is about right. So next, we're going to look at the different humidifier types that are available and some of the pros and cons of using them. So firstly, we're going to look at an electrode boiler humidifier. Now, they were historically very, very common, and we still sell lots of them. But before we go and specify an electrode boiler, we really ought to understand some of the potential shortcomings of utilizing an electrode boiler. So to do that, we'll just look at how it works. So our electrode boiler, the heart of it is a polypropylene cylinder. And inside that cylinder are a series of electrodes. Here you can see them. When we get a demand signal, water fills up this cylinder to a level that's relative to the control signal. So if I've got 5 volts of a 0 to 10 volt signal, it'll fill up a certain amount and cover a certain proportion of those electrodes. And then current will be passed through the water, and we'll heat the water up and boil it, changing its state from a liquid into a vapor, and then steam merrily comes out of the top and goes through some flexible tubing or hard drawn copper into a steam pipe and is injected into the air handling unit. Well, that seems pretty straightforward. What could go wrong? Well, there's a couple of things that we need to consider. The first one is modulation. So if I want to vary the output, I've got to change the amount of water that's in the cylinder. I've either got to boil some off or I've got to put some in. So if I put some in, it's going to take me off the boiling point. I won't be producing steam. So because of the way that it modulates, it will give you plus or minus 10% RH control. So for a comfort application, great. But it will only modulate between 20 and 100% of its output. So in a mid-season application, it may just be on-off control. Still going to give you typically plus or minus 10. The other thing to consider is the water quality. Because as we produce steam inside this cylinder, any minerals will get left behind and will form a scale on these electrode plates. And eventually, these electrode plates will scale up with so much scale and will deteriorate. And eventually, the unit will say, oh, do you know, I'm so full of scale now, I can't produce steam anymore. And I've lost my connection.
No, we're still with you, Dave. We can hear and see you.
My apologies, just come off my side. So, as we go back to our electrode boiler, as we're producing steam, we have a concentration of minerals, and after a certain amount of time, this unit will say, I can't produce steam anymore, and at that point, the unit will alarm out, and you have to take the cylinder out and you throw it away and you buy a new one. And they're up to £500 to £600 now. Prices have increased to replace a cylinder. So they're not the cheapest thing to replace. So the big question is, how long is my cylinder going to last before I have to chuck it away and buy a new one? Well, again, that really relies on the conductivity of the water. And to give you a couple of good site examples, a good example was the Kodak factory up in Leeds in the north of England. Water quality was pretty good. They got 350 microsiemens water quality, and they were using them 6 to 8 months of the year. And typically they would change the cylinders once a year. That's a pretty good application. Now we did have one project that at the other end of the scale, where it was a site in London running on mains London Water, and they were running them full belch on mains London Water, and they were averaging about 9 to 12 days before the cylinder was toast. So they've got a real maintenance issue here. So they tried to solve this problem. They knew that hard water was the issue, so they installed a water softener. Now, a base exchange water softener is going to take the calcium out, but it replaces it with sodium. And that does a couple of things. Firstly, softened water foams at high temperature. So that gives a false reading on water level, so your control goes out. And also, it's corrosive. It eats the electrodes. And indeed, we're not taking any minerals out, we're just replacing them with a different kind of mineral. So that didn't help them. Softened water, not perfect for electrode boiler. The next thing they tried to do was they tried to install, in fact they did install, a reverse osmosis water treatment plant. Now, a reverse osmosis water treatment plant is going to take 97–98% of the minerals out of the water. Great. I never have any minerals forming in my cylinder. The downside is if you feed an electrode boiler with RO water, you'll never produce any steam because if you take the minerals out of the water, it won't conduct electricity. So they were back to square one. So the moral of the tale is that before you tick a box on an AHU spec saying I want an electrode boiler, just a standard humidifier, look at what options are available. Will it give you the controllability that you want? And is it suitable for the water that you have? Now, they are pound for pound the cheapest form of humidifier out there. And you can get high steam outputs out of them. They start at 5 and they go up to 160 kilos an hour in 4 boiling chambers. And they're simple and quick to maintain. Just got to drain them down and change the cylinder. You need to clean them out as well. But typically they're a really good unit. But you are going to be using any electrical power. So again, for every 100 kilograms of steam, 75 kilowatts. There's a high maintenance commitment. And again, that is down to the water quality. You've got to change the cylinder. You've got to clear out the drain pump. Then that's something that's got to be allowed for in a maintenance regime. And of course, you've got to pay for the replacement spares. So we've got to change those cylinders. Again, could be £400, £500, £600, depending on the size of the cylinder. But because it's using electricity, we do have the potential for the use of renewable energy. So critical thing to remember is what's my water quality and what's my control requirement. Now, if this doesn't meet your requirements, then you would go to a resistive heater humidifier. Now, capital cost has just gone up by about 2.5 times to go for a resistive heater, but it's a different beast. It's a different machine completely. Now, you can see on the diagram here that we no longer have a plastic cylinder because we're using resistive heating elements. So the water isn't live. We're not passing current through the water. So how this unit works is that when we get a demand signal, water will fill in this cylinder and it will be controlled. The water level will be controlled between a series of float switches. So we will always control the amount of water. But to get modulation out of it, we'll pulse electricity to these heating elements at a rate relative to the control signal. So if I've got a 0 to 10 volt control signal going to this unit at, let's say, 5 volts, it'll pulse on and off every other cycle in a 10 cycle period. And it will modulate from 0 to 100% of its output because I can change the rate of that pulsing via those solid state relays. So it will give me much tighter control. Even though I'm still doing a dilution cycle drain, I'm controlling that water level, so I don't come off the boiling point as much. But by modulating the energy that goes to those heating elements, it's going to give me that plus or minus 5% control. Now, if I want finer than that, I can actually use RO water with these units. So because I'm not relying on conductivity, if I'm in a hard water area, I can feed RO and reduce the maintenance requirements. And that will give me between 1 and 2% RH control because I'm not having to do any dilution cycles. Also, with the resistance heater such as this one, you have inbuilt scale management. So as scale forms on these heating elements, as the element expands and contracts, the scale will crack and fall off and be then collected into the scale collector at the bottom of the unit, which periodically can be drained down, emptied and put back by the maintenance engineer. So we're never having to buy another plastic cylinder. I've still got to maintain the unit, but I don't have such high spares costs. So with a resistance heater, we're going to get that close control. We're not relying on conductivity. So in a low conductivity area, I can use them. And in a high mineral content area, if I want to reduce the amount of maintenance, I can feed it with RO water. Steam capacities are very similar. They start at 5 and they go up to 160 kilos an hour with 4 boiling cylinders. I do have to consider, of course, the energy consumption because for every 100 kilos of steam we're producing, it's 75 kilowatts. And of course, there is a regular maintenance commitment. Again, we can use renewable energy. So again, it's really important to specify the type of humidifier that you're going to be using because the ramifications of getting the wrong one are really significant. Now, you can have a gas-fired humidifier. It's not just the electric humidifiers you can have there. This is a gas-fired humidifier. And here, simply, we have a boiling chamber that will fill with water that's attached to a heat exchanger that's immersed in it as an immersed heat exchanger. And that heat exchanger is attached to a burner, and we fire hot gases into the heat exchanger and heat the water up and produce steam at atmospheric pressure. Pretty straightforward. We control the output by varying the burners, so we do get typically plus or minus 5 to 10% RH control. And for applications such as a spray booth or something like that, it's very common to use gas because we get consistent high demand levels and high airflows, so high steam duties. So the run cost for using gas is better than for using electricity. They start though about 15 to 20 kilograms an hour and go up to 260 kilograms an hour, again lending themselves to those larger duties. Now, with all of these units, we're only producing steam at atmospheric pressure, so that reduces the length of the pipework that you can have between the humidifier and the duct, because the only thing that's driving the steam from these units is the expansion that happens as water changes its state from a liquid into a gas. That's what's driving it through that pipework. It's expanding by over 1,000 times. Of course, if you make that pipework too long, then that steam will start to collapse and you'll lose your duty. There are some other types of humidifiers out there. There are steam-to-steam units, and this is really something that you see in pharmaceutical applications, and it's just basically a big heat exchanger. So you get live steam coming into one side of it, and a clean water supply going to the other, and we produce steam at atmospheric pressure. Low energy use because we've already got the steam going around the plant, and have high steam outputs, up to 200-300 kilos an hour. And install costs and footprint are very similar to the gas units. Of course, you don't have to consider any fluing. And plus or minus 5 to 10% RH control. Again, it's just a big heat exchanger. You may, though, want to use that live steam, and you can do that by taking live steam, taking through a pressure reducing valve, letting steam come into a valve body. In that valve body, condensate will be separated away, and in this case, taken away in an inverted bucket steam trap. And then steam, when the valve opens, will come into this header, to these tubes, and you can see you've got lots of little holes here that the steam's going to come out of, and then any condensate will be taken away through this little thermal trap and back into the condensate system. Low energy use, you're just utilizing an existing steam supply. High steam outputs, they start at 5 and they go up to almost 1,000 kilos an hour for these units. The only thing you really need to consider is whether clean steam is required. If clean steam is required, this valve body must be made of stainless steel, whereas as a standard, it will be supplied as cast iron. When we talk about steam distribution, how do we get the steam into the duct? Well, very simply, it's a stainless steel tube with holes in it. Flexible steam hose will connect on or to this port, and the tube will be mounted onto the side of the duct or air handling unit, and then steam will come out of these holes. The thing we have to consider is the absorption distance. So how long will it take for that steam to be completely mixed with the air? And that will depend on a number of factors: air-on temperature, duct dimensions, velocity, the number of holes in the steam pipe, various other factors. Typically, you're going to see absorption distances around 1 to 1.4 meters. But we need to think that if there's anything else happening after that distance, because if there's a HEPA filter, I need 2.5 times that distance. Well, all of a sudden, we may have a very long section requirement, and that may not always be possible. When we are faced with that scenario, we use a short absorption distance manifold. And basically, we're putting lots of tubes in the airflow with lots of holes and introducing steam across the whole cross-section of the duct or air handling unit. By doing that, we reduce that distance. Now, we may not have a ductwork or air handling unit to put air into. It may just be something like a comms room or a switch room. And for something like that, we can just use a fan unit for direct room applications, where we're just going to put we're going to blow a small amount of steam directly into the space. So how we get the steam into the duct or into the space, it needs some evaluating as well. So next, we're going to turn to adiabatic systems. We've looked at steam. When we look at adiabatic systems, there are a number of choices, as there are with steam systems. But our first port of call would be an evaporative media humidifier. Here you can see one. It's built to match the internal dimensions of the air handling unit, and it's pretty simple. You have a tank of water in the bottom there. When we get a demand signal, water is pumped through this hydraulic module, goes up through these tubes, and there's an encapsulated spray bar in the top of the unit that then cascades water over this glass fiber porous material, and then is circulated round and topped up as required. So pretty simple in its operation. We can get high humidity outputs out of these. They start at 30 and they go up to, well, almost 1,000 kilos an hour on really large units. The beauty here is that they're low energy. About 270 watts runs this, because all you're running is a panel and a hydraulic module. It's low maintenance, it forms part of the water system, so it has to be chlorinated once every 6 months. But apart from that, the flushing of the material should keep any mineral deposits on the material to a minimum. And there's no evaporation distance, because all the water is evaporated off the surface, so there's no water droplets. We also have a UV light installed in the tank there, so we get a high kill rate of any bacteria. And when we don't have any use of, no demand, the whole unit will just dry down, so we don't have any bacterial growth. We do, though, have to consider preheating the air, of course, because it's an adiabatic process. My limiting factor is controllability, because I'm either turning on or off certain sections of this humidifier. So I'm either running one or a number of these pumps. So typically it will give me plus or minus 10% RH control. If I want to do better than that, I would go to a high pressure system. So different system here completely. So with a high pressure system, we go through an RO plant, we take the minerals out of the water, and we then pump that RO water at high pressure to a spray manifold bar with a series of nozzles mounted on the bars. And when we get a varying demand signal, we will turn on or off certain nozzles or certain bars on this manifold. And by doing that, I can get plus or minus 5% RH control. There are some things to consider though. Of course, I'm going to be using RO water. And as soon as we do that, we're using twice the amount of water, because you put 100 litres in, 50 litres will go to the RO, to the humidifier, and 50 litres will be flushing the RO membrane. So you're using more water. And you've got a mist eliminator there to prevent any moisture going into the airflow. And also you're going to require a stainless steel section in that air handling unit, because it's a wet section. So you're going to have a stainless steel section with a drip train. But because we're modulating via turning on and off various rows of this manifold, I will get plus or minus 5% RH control. And with this unit, I can control up to 4 air handling units from one system. If I want to do better than that, I can utilize both types of technology with a hybrid system. Well, a hybrid system is going to take mains water, it's going to run it through a softener and a reverse osmosis plant, and a silver ion exchange, and we're going to take that water to a nozzle array, where we've got many, many more nozzles spread across the whole cross-section of the AHU. And I can turn off sections of these nozzles to give me many more stages of control. And I can have up to 31 stages of control from systems such as this. So it will give me plus or minus 2%. But the clever bit about it and the way it's using two types of technology is that we're spraying water, but then any that hasn't been evaporated gets caught on a ceramic matrix, which then evaporates it off as the air travels over it in the same way that an evaporative humidifier does. So we're not getting the wastage that you do with a traditional high pressure system. So I can have a short section length, 600 mil between those two sections. I've got to have a stainless steel section in there because it's a wet section. but it will give me that close control and utilize the adiabatic system. Alternatively, you could have direct air spray systems. Here you can see a direct air, a compressed air and water system. This is spraying a print room to humidify the air. Great for an area where you don't need zonal control and noise isn't an issue. So a production area, somewhere like that, absolutely perfect for. Textile mill, great. Printing, perfect. Very simply, it's taking a compressed air and water supply, modulating it and taking it through lines and then attaching a nozzle to those lines, and inside the nozzle the compressed air and the water is mixed together. We get a very fine spray going into the space. And here we would consider the nozzle size and the height of the mounting the nozzles as to where we would mount the lines. Again, limiting factor is there's no zonal control. So one area it will work from one humidity stat or sensor. If you want zonal control, you have to go to a high pressure system. And here you can see a high pressure system in the supermarket. With a high pressure system, we would take RO water and we put it, tube it to a number of heads, and we'd almost have like a ring main going around, and we would tap into that ring main and spray out into spaces. Now, the way that we get zonal control is by having local sensors or stats and local valves. So we can allow water to go to a number of these spray heads in the system. So I can get zonal control, great if you've got an area where you've got two climatic conditions, or indeed you've got areas that are subject to solar gain that could alter your controllability. So the theme here really is choosing the right type of humidifier for the right application. And there are many different requirements, some of which we've talked about today. So again, thank you very much for bearing with us through the webinar. There's lots of resources online, all the technical files, BIM files, spare parts list. There's even a psychrometric calculator and solutions for every humidification need on www.condair.co.uk. And of course, we have a number of area sales managers spread across the UK and Ireland. We'll be very happy to help with any of your applications. So we at Condair, we design, manufacture, install, commission, service and site surveys and risk assessments, anything from moving a box to an air handling unit manufacturer to doing a full turnkey end user supply, install and commission service. Thank you. Well, I'd like to open it up, see if you have any questions.
Right, and Dave, yeah, thanks very much for the presentation. Yeah, there's been loads and loads of questions. So what I'm going to do is I'm going to put a few to you, Dave, and then what we'll do is, apologies if I can't answer everybody's, but what we will do is we will come back to you afterwards by email to answer your questions. So what I'll start with is a question which asks, in a world where we have global warming and a shortage of water at a time when we require cooling, should we be using evaporative cooling?
Well, I think you've got to compare it to the other methods of cooling. When you compare the energy costs of a traditional legacy cooling application, let's say you've got a telecoms room for cooling, when you've got machinery that you have to cool it, by using evaporative cooling instead of traditional direct expansion, we've seen applications where that energy requirement is reduced by 80% by using evaporative cooling. So again, it has to be applied correctly. But where cooling is required, adiabatics can make a lot of sense, as opposed to just using traditional legacy, where for every kilowatt of cooling, you're going to be using 30 watts of energy. Whereas with evaporative cooling, for every litre of water that you're evaporating is going to give you 680 watts of cooling. So it's you can see the comparison is direct. You're getting almost over twice of the cooling for adiabatics as opposed to traditional cooling methods.
Brilliant, thanks, Dave. The next question I have is, any suggestion on how to control the relative humidity when I do passive cooling through window opening?
Well, it's really difficult actually to do. As soon as you do that, you are then losing control of the environment, because your ambient relative humidity is going to be a direct reflection of the absolute moisture content of the air outside. So as soon as you do that, you might as well try and humidify the whole of the town that you're in. So I would say, when people say I want to humidify a certain area, well, it's like trying to put a pile of water in a corner of a room. As soon as you let go, it spreads out, it dissipates. So with passive cooling, yes, you're going to be opening the windows and you're getting some free fresh air there. The only good side is that if you're doing that, the colder air will probably be more humid, so the relative humidity should be probably better off. So it very much depends on the absolute moisture content of the air that's outside. But I go back to the point that as soon as you start to open those windows, you're losing control of the environment, and you're absolutely reliant on the absolute moisture content of the air at ambient conditions.
Okay, that's another good question here. It's two-pronged, but what this gentleman is asking is softened water good or necessary for resistive humidifiers? And if so, will it reduce the maintenance?
We don't generally recommend using softened water in humidifiers. In theory, it's okay if you can blend it. Now, softened water, as I mentioned, you're not taking out any minerals. You've got the same amount of minerals. You're exchanging calcium for sodium. So that can have an effect where you get more corrosion because it's a saline solution. But you're not going to reduce the amount of maintenance because you've still got the same amount of minerals in the water. So your maintenance period for the resistive heater is going to be pretty much the same. You're still going to have to empty those minerals out, as you can see in the little photo there, where the lady is emptying the minerals out, because we're not changing the amount of minerals, just changing the type of minerals. In fact, instead of getting a hard scale coming out of there, you're going to get a really thick sludge from the salt. So it doesn't alter the maintenance frequencies.
Okay, we'll make this the last question for the seminar because we do have lots of questions. So we will. I do promise we'll get back to everybody. But this one is: how far can steam travel in ductwork? Would you need a couple of humidifiers at different points rather than one at, say, the main plant room if the design entails very long pipework runs, ductwork runs even?
Okay, that's a good question. And the short answer is no, because when you've put the moisture in the air and it's evaporated into the air, then the air is holding it. So whatever condition you've got after steam absorption, that's what you're going to get. The only restricting factor is the distance where the humidifier is located to where the steam pipe is located, because that's limited by the pressure exerted when the moisture changes its state from a liquid into a gas. So it's the expansion that happens as that liquid is turned from a liquid into a gas that's driving the steam down the steam pipe. Once it's mixed in the air, it's there, and it's not going to go anywhere. It's going to stay in the air. So no, you don't need another humidifier closer. What you need to do is ensure that the steam pipe is located within 4 meters of the humidifier. So you're reducing that distance. Once it's in the ductwork, it's absolutely fine. Once it's mixed with the air, it's fine.
Okay, I am going to ask one more question because it has been asked so many times here, and it is what's the implications and how do we mitigate the risk of direct involvement of Legionella if we use evaporative cooling?
Okay, that's a really good question. With evaporative cooling, well, for you to get Legionnaire's disease, you need to breathe in a water droplet that contains the live virus pneumophilia, Legionella pneumophilia. So when you're working with an evaporative system, there is no water carryover. The reason that you have no water carryover is that the water is evaporated off the surface. So there's no water droplets coming off that unit that's being suspended in the air that you can breathe in. There isn't any. It's evaporated. And we go further than that. We don't want any biological growth inside the unit anyway. So as I mentioned, we have a submerged UV in the tank, and that kills any bacteria. We don't have any stagnation because the water is constantly moving. And also, when we don't have a demand signal for a number of hours, we drain the whole unit down. And that's how we prevent bacterial growth in the unit, and indeed how you prevent moisture, any bacterial growth getting into the airflow, because there's no transition method. You're only getting liquid in its vaporous, in its gaseous stage or gaseous state going into the airflow. So there is no bacterial transference.
I think, yeah, like I said, there's so many questions. We will come back to you guys, but I think as we're getting towards the full hour now, I'll hand it back to you, Dave.
Excellent. Thank you very much to everybody for joining the webinar. It's really appreciated. We've had a tremendous turnout. Again, we will get back to you with any questions. And if you do have any applications, please feel free to drop me a line or give me a call, and our team will handle them with pleasure.